Hi everyone! Today we're going to be talking about the real number system and properties of real numbers. Our objectives for today are that students will be able to classify real numbers and you'll be able to identify properties of real numbers. Let's get started. Why is it important that we learn about the real number system? Here's an example of when we would use this in real life. The Central High School boosters sell snacks and beverages at school functions. The items are priced the same to make determining the total cost easy. You can use the distributive property, which is a property of real numbers, to calculate the total cost when multiple items are purchased. When we talk about real numbers, we use the letter R and a capital R to represent real numbers. Real numbers consist of the following sets of numbers. So irrational numbers are real numbers, and rational numbers are also real numbers. Irrational numbers are numbers in which the decimal form never terminates and does not repeat. So common examples of irrational numbers are pi, because it goes on forever, and non-perfect square roots. So basically, irrational numbers are numbers that do not terminate, so they go on forever and ever and ever, like pi, and they do not repeat. So if a number repeats, if it's 0.39393939, that's a repeating decimal. So that would be a rational number, not an irrational number. So it can't go on forever, and it can't repeat. Now, a rational number, rational numbers are numbers in which the decimal form either terminates, so it ends, or it repeats. Rational numbers can always be written as a fraction, a over b, where a and b are integers. Now, different kinds of rational numbers are integers, so we've got negative whole numbers, 0, and whole numbers. Whole numbers, which is 0, 1, 2, 3, 4, and then natural numbers are like your counting numbers, 1, 2, 3, 4, and 5, and so on and so on. Alright, so organizing the real number system. First, let's break down what is the letter that represents each set, and some examples of each set. So first of all, we've got irrational numbers, and we use the letter I to represent irrational numbers. Some common examples of irrational numbers would be pi, like we had talked about before, and the square root of non-perfect squares. So for example, the square root of 5. Let's see, the square root of 72, square root of 41. All right, these are all irrational numbers because they go on forever and they do not end and they do not repeat. Now, rational numbers. We already used R to represent real numbers, so rational numbers, we use the letter Q to represent rational numbers. Some examples of rational numbers would be decimals that end or terminate, so 0.34. Let's see, if it's a mixed number, 1 and 5/8, that's a rational number. 0.2 repeating, because it repeats, it goes on forever, all right? As well as negative fractions, so negative 7/11, that is a rational number. Integers, the letter we use to represent integers is the letter Z, all right? And I always put a line through the Z so then it doesn't get mistaken for a 2. Integers include whole numbers, all right? And it also includes negative whole numbers and 0. So some common examples of integers would be 7. 7 is an integer. We can also say the square root of 100 is an integer because the square root of 100 is 10. 0 is an integer. 8/4 is an integer because we can simplify that to 2. These are all common examples of integers. Whole numbers, we use the letter W. Pretty simple and easy to remember. Some examples of whole numbers. It includes 0, all right, and then it's positive whole numbers. So if we said 20/4, that is a whole number and a rational number and an integer, all right, because we can simplify it to 5. Let's see, the square root of 16 is a whole number because that can get simplified to 4. And 90, any whole positive number is a whole number, all right? Last but not least, natural numbers. Natural numbers, easy to remember, we use a capital N to represent natural numbers. And natural numbers are your counting numbers. So what you learned in kindergarten, 1, 2, 3, 4, 5, and so on. And it does not include 0. So 10 is a natural number. 47 is a natural number. Square root of 9 is a natural number because we can simplify that to 3. As well as fractions that we can simplify to whole numbers as well, like 34 over 2 can get simplified to 17. Alright, now we can use this fancy little handy-dandy Venn diagram here to help us organize all of our real numbers and the real number system. So, first of all, we know that all of these are real numbers. So we can put an R on the outside because everything in this rectangle is a real number. Now, if we're talking about, now we've got two different kinds of real numbers. We've got irrational numbers and rational numbers. So we're going to say this tiny little box over here, this little circle, is irrational numbers because they're kind of on their own. They're their own separate thing. They're still real numbers, but they're separate. Then we've got rational numbers, and we're going to put that Q to represent rational numbers on the outside of our circle. Then we can say integers go within that because integers are also rational numbers and they're also real numbers. Then we can put, whole numbers in the next little circle because they're also rational numbers and integers and real numbers. And then last but not least, we've got natural numbers on the inside because a natural number is also a whole number, is also an integer, is also a rational number, and is also a real number. Alright, so this is a nice little handy-dandy Venn diagram to help us remember the relationship between our real number system. Alright, so let's practice naming all the sets to which each value belongs. Number 1, we've got negative 10. Now, negative 10 is an integer, so we're going to write Z for integer. If it's an integer, that means it's also a rational number, and we use Q to represent rational number. And if it's a rational number, that means it's also a real number. So, negative 10 is an integer, rational number, and real number. That's all the sets to which negative 10 belongs. Number 2, we've got the square root of 30. Square root of 30 is going to be an irrational number because if we plug that into our calculators, we're going to get a decimal that goes on forever. So we say it's an irrational number, but it's also a real number as well because all irrational numbers are real numbers. Number 3, we've got 1 and 7/9. Alright, 1 and 7/9, because it's written as a fraction, it's a mixed number, alright, we would consider this to be a rational number. And if it's a rational number, it's also a real number. Number 4, we've got 24 divided by 8, or 24/8. This equals 3. Alright, so we always simplify it first. Now, 3 is a natural number, it's a whole number, it's an integer, it's a rational number, and it's a real number. Alright, so we're using that chart to help us and using our notes to help us determine if it's a natural number, that means it's also a whole number, integer, rational, and real number as well. Number 5, we've got 2.48. We've got a decimal that terminates or ends. Therefore, we would say that 2.48 is a rational number, and if it's a rational number, it's a real number as well. Alright, it's not an integer, whole, or natural number because it's a decimal. Number 6, we've got negative square root of 81, which if we simplify this, we get negative 9. Negative 9 would be considered an integer because negative whole number. Alright, so we can put a Z for integer. If it's an integer, that means it's a rational number. And if it's a rational number, that also means it's a real number. Alright, now what I want you to do is pause the video. When I say go, pause your video and try to do numbers 7 through 12 on your own. When you come back, I'll have the answers written on the screen. You can check your answers and we'll go through them together. Alright, so go ahead and pause your video now and try numbers 7 through 12. Alright, so you can go ahead and check your answers for numbers 7 through 12 and we'll go through them together right now quickly. So number 7, we've got pi minus pi. If we simplify that, we get 0. Now 0 is a whole number, an integer, a rational number, and a real number. Number 8, if we simplify the square root of 16 over 25, these are both perfect squares, we get 4/5. 4/5 is a fraction, all right, and that means it's a rational number and a real number. Number 9, we have a decimal that repeats. Repeating decimals are rational numbers, and rational numbers are also real numbers. Number 10, we've got 109. That's a whole number. It's a natural number. So natural number, whole number, integer, it's all three. We know if it's a natural number, it has to be all of these as well. Rational number and real number too. Number 11, we've got -8/3. It's a fraction. It's negative. It's just a rational number. And if it's a rational number, it's a real number. And last but not least, number 12, we got square root of 7 divided by square root of 7. Anything divided by itself gives us 1. And 1 is a natural number, and if it's a natural number, it has to be a whole number, integer, rational, and real number as well. All right, now we're going to be talking about the properties of real numbers. So we've got 5 different properties: commutative, associative, identity, inverse, and distributive. And we're going to talk about each of these 5 properties as it deals with addition and with multiplication. So first, let's start with the commutative property. Commutative property, simply stated, just means when the order switches. Think of if you're commuting somewhere, right? If you're driving somewhere, you're commuting somewhere, you're moving. So the order is moving. So when we're dealing with addition, what this means is if we have A plus B, we're just switching the order. So we're saying B plus A. That's the commutative property of addition. When we're dealing with multiplication, it's pretty much the same thing, but we're multiplying. So A times B, we're switching the order. Now it's B times A. And with addition and multiplication, order doesn't matter. So if we switch them, we'll still get the same answer. Now, associative property means grouping, so who you associate with, right? Your group of friends. So associative property is when we change the grouping of the variables. So an example with associative property is if we first have a group of A plus B, and then we add C on the outside. To change the groupings, what we would say is A plus B plus C. So this is the associative property of addition because the groupings change. Now with multiplication, it's very similar, but we just put a multiplication symbol in between instead. So if we've got A times B times C, it's the same thing as A times B times C. Now, identity property. Identity property is where it equals the same value. So if we have A, what do we add to A to equal A? So simply stated, if we have A and we want it to equal A at the end, we would just add 0. That's the identity property of addition. Now the identity property of multiplication. If we have A and we want it to equal to A, what do we multiply it by? We would multiply A by 1 to equal A. That's the identity property. We want it to equal itself. So what do we add or multiply by? Next we have the inverse property. So the inverse property of addition is where we take A plus, and we just say plus negative A. So the inverse means the opposite sign in addition. So if it's positive A, we add negative A. And then it equals 0. That's the inverse or the additive inverse. The additive inverse is the opposite sign. Now the multiplicative inverse, we've got A. Multiplicative inverse is where we flip it. So we put it underneath 1. So A times 1 over A, that's the multiplicative inverse, and that equals 1. Inverse property of addition and multiplication are slightly different, so it's important to keep them straight. And then last but not least, distributive property uses both addition and multiplication, and you should all be pretty familiar with the distributive property. So distributive property, if we've got A times b plus c. We can rewrite this as a times b, so we distribute the a to the b, plus a times c. All right, so here's the properties of real numbers. All right, so for the most part, as we do notes for this year, what we're going to do most of the time is we're just going to do the odds. So the reason we do this is because it's almost always not necessary to go through every single example. Just doing the odds will give you a good idea of what we're learning. Also, we just don't have the time to do all the problems. However, I highly encourage you to do the evens if you ever feel like you need extra practice, and I'm more than happy to check your answers because I always have the answer keys to every single problem, including the evens. So if you want to come in after school or at support or at lunch if I'm there and check the evens, best time to probably do that would be at support. You're more than welcome to, and I highly, highly encourage you to do those evens if you ever feel like you need extra practice. All right, but for now, we're going to do the odds and we're going to name the properties. So what I want you to do is I want you to pause your video when I say go and try to name the properties of each of these. So is it the commutative property of addition, the identity property of multiplication? So be sure not to just say what property is, make sure you say of addition or of multiplication, all right, because that's very important as well. So what you're going to try to do these on your own. When you come back, I'll have the answers written on your screen and we will go through them. So go ahead and pause your video now. All right, so here's the answers to 13, 15, 17, and 19. So 13, we've got the associative property of multiplication because the groupings are changing and we're multiplying. So associative property is when we're changing the groupings. Number 15, we're saying the additive inverse of 7y is negative 7y. So this is the inverse property of addition, or the additive inverse. 17, we're changing the groupings and we're adding, so it's the associative property of addition. And number 19, it looks a little different than what we're used to because it's switched around, but this is the distributive property because we're saying 3 times m, 3 times n, and that gives us 3m plus 3n. So this is the distributive property. All right, so now we're going to name the additive and multiplicative inverse for each number. And we're going to do all 4 of these because it's a little bit of a tricky concept and I want to make sure you understand this. So 21, we've got negative 8. The additive inverse, so additive inverse means switch the sign. So the additive inverse is positive 8. The multiplicative inverse is when we put it underneath 1, right? We flip it. So right now this is negative 8 over, over 1, right? So we flip it and it becomes negative 1/8. Number 22, the additive inverse, change the sign, so it becomes negative 2/3. Multiplicative inverse, flip it, so 3 over 2. Number 23, we've got 6w. Additive inverse, change the sign, so it becomes negative 6w. Multiplicative inverse, it's over 1, flip it, so 1 over 6w. Last but not least, number 24, square root of 10. Additive inverse, change the sign, so it becomes negative square root of 10. And here's the tricky part for the multiplicative inverse. Right now, this is the square root of 10 over 1. If we switch it, we get 1 over the square root of 10. However, we can never have radicals or square roots in the denominator. So what we have to do is multiply the top and the bottom by the denominator in order to what we call rationalize the denominator. We got to get rid of the radical in the denominator on the bottom. So if we multiply the top and the bottom by square root of 10, we get square root of 10 on top, and on the bottom you get square root of 10 times square root of 10 gives you square root of 100, which we can simplify to 10. So the multiplicative inverse of square root of 10 is the square root of 10 over 10. So that one's a little trickier, which is why I wanted to do that even with you. All right, our final property is the closure property. So the closure property states that a set is closed, and we say closed under an operation, if the operation always produces an element of the same set. So it has to, if it's closed under addition, that means a rational number produces a rational number. All right, the same set. If an element outside the set is produced, then the operation is not closed. So we've got 4 problems here. We're going to answer either it's a true statement or a false statement. If it's false, we're going to give a counterexample or give an example that proves it to be false. So number 25, integers are always closed under multiplication. All right, this is true because if we multiply an integer by itself, so say we've got, let's see, if we've got an integer would be -3 times -3. We're going to get +9. That still produces an integer. It produces the same set. So this is a true statement. There's no example that we can come up with that proves this to be false. So we would write true. All right. Then, let's see. Let's erase this real quick. Number 26. It states irrational numbers are closed under subtraction. This is a false statement, all right? And the reason this is false, I can come up with one example. So an irrational number, the easiest irrational number to remember is pi. So if we say pi minus pi, this equals 0. And 0 is not an irrational number. 0 is a rational number. It's also, what else? It's also a whole number, an integer, all right? It's a rational number, not an irrational number. So this is a false statement. 27, whole numbers are closed under division. This is also a false statement because we can come up with a counterexample to this. A whole number divided by a whole number. How about 2 divided by 3? This equals 0.6 repeating. 0.6 repeating is not a whole number. All right, it's a rational number, but it's not a whole number. So a whole number divided by a whole number produces a rational number, produces a number in a different set. So this is a false statement. And last but not least, odd numbers are closed under addition. All right, this is false as well because if we add 2 odd numbers together, say for example 3 plus 5, that equals an even number. So that is a false statement, and we provided a counterexample to prove it to be false. You could have come up with different counterexamples, and that's totally fine. These are just the counterexamples I came up with, all right? So there's not just one right answer when it comes to the counterexamples as long as it works. All right, so I hope you learned a thing or two about properties of real numbers and the real number system today. And be sure to save any questions and ask me tomorrow. Otherwise, I hope you guys have a great day.